Imagine standing in a landscape so enormous that the horizon seems endless. There are no towering mountains or dense forests here. Almost nothing interrupts the view, except fields stretching for miles. This stillness ends at the grain elevators and rail spurs. Freight trains stretching over a mile long connect these fields to a global distribution network. Those railways transport the region's wheat, corn, and soybeans to industrial coastal terminals and deep water ports. A harvest in Kansas can ultimately supply flour to communities thousands of miles away. To produce yields on this scale, farmers use fleets of GPS-guided combines, automated planters, and moisture sensors. Computer-controlled equipment covers thousands of acres, requiring only a fraction of the human labor that agriculture relied on a century ago. Technological efficiency is only the final step. The output of this region relies on ancient biological and geological resources buried beneath the surface. This map illustrates the environmental constraint dictating local agriculture, a strict east-to-west precipitation gradient. In the eastern section, climate delivers regular rainfall supporting thirsty crops like corn and soybeans. Moving west, the environment becomes significantly drier. Without reliable rain, the landscape shifts towards grazing and livestock. The soil itself was built over millennia. For thousands of years, native prairie grasses covered this land. As their root systems continually grew, died, and decayed, organic material slowly accumulated into a thick, nutrient-dense layer of topsoil. Millions of American bison maintained this ecosystem. By constantly moving and grazing, they stimulated grass growth and naturally fertilized the expansive landscape. Indigenous peoples lived within and actively managed this environment. For numerous Native American nations, the bison and surrounding prairie provided food, tools, homes, and clothing. When European settlers moved westward in the 19th century, they began plowing this ground. By cutting into the sod to build homes and plant wheat, they tapped into a biological savings account that took thousands of years to compound. A geological cross-section of the Western Plains reveals the region's critical resource, the Ogallala Aquifer, a subterranean water reserve ranking among the largest in the country. This ancient pool gathered over geological epochs. It is essentially static, receiving almost no recharge from modern rainfall. In the 20th century, powerful new drilling and pumping equipment gave farmers access to this deep reserve. With a flip of a switch, they could pull thousands of gallons to the surface, allowing them to grow water-heavy crops in naturally arid zones. The visual footprint of this technology is unmistakable from above. Center pivot systems draw from the aquifer, painting circular patches of green across the dry landscape. But the underlying math is unforgiving. Millions of gallons are being pumped out of the aquifer every day, draining the reserve significantly faster than natural geological processes can ever replace it. We already have a historical record of what happens when agricultural expansion pushes past the physical limits of this landscape. By the 1930s, decades of intensive plowing had eradicated the deep-rooted native grasses that held the prairie together. When a severe, multi-year drought struck, the exposed dirt lost all structural integrity. High winds caught the loose earth, lifting millions of tons of topsoil. Black blizzards swept across the states, suffocating livestock and burying entire farms. The Dust Bowl proved that fertile soil is a finite, fragile resource. The resulting economic devastation forced the adoption of contour farming, crop rotation, and windbreaks to keep the remaining dirt anchored to the ground. Today, the region faces a quieter crisis. The steady depletion of the Ogallala Aquifer presents a structural threat to the future of the breadbasket. Changes in global temperature patterns are acting as a threat multiplier. As summer heat intensifies and seasonal droughts drag on longer, crops require even more moisture, forcing an even heavier reliance on the shrinking groundwater supply. Farmers are actively adjusting to these constraints. Many are transitioning to drought-tolerant crops like sorghum, reintegrating cattle into their field rotations, and utilizing precise soil data to eliminate water waste. Yet, no matter how efficient precision sensors become, software cannot manufacture rainfall, and heavy machinery cannot refill ancient subterranean lakes. The Great Plains is a complex, fragile ecosystem with strict physical boundaries. The continued stability of America's food supply relies entirely on our ability to respect the invisible limits hidden beneath the soil.